Embedded safety and security, I'm going to take a use case from the ADAS perspective, and given I come from a semiconductor background, I'll be, giving you a perspective from, a tier 2 perspective. So let's start with the agenda, and as we always see, we need to first know, why we need this presentation, and for example, in this case, why do we need a new technology? Why imaging radar is so important today, and why the automotive industry needs it. And then we look at, given most of you are not into, from the ADAS perspective, what is actually an imaging radar and how it differs from the current radar that's there in the market. And then we look at, what are the challenges to build such an imaging radar, and the most, important aspect of this summit, what are the functional safety and security considerations to build such an imaging radar, and the last 5 minutes for the Q&A. But before I start, I want to ask the audience one simple question. More than 90% of the cars in US have a system called AEB, the automatic braking system. How many of you believe that the current AEB system is safe? Please raise your hand if you think it is safe. Okay, looks like the audience is pretty aware that the current systems are not safe. But before, let's go into a very recent news report, which talks about, what is the state.
Automatic braking has become a standard feature in about 90% of new cars.
But a new report finds that technology doesn't always work. CBS 2's Danya Backus has more on what drivers need to know.
Test video from AAA shows how automatic emergency braking can prevent a rear-end accident. The feature uses cameras and sensors to detect a vehicle.
And it will apply the brakes if the driver does not.
AAA's Megan McKernan was part of the research that tested vehicles from 4 automakers.
And we found at 30 miles an hour, 85% of the time the vehicle either came to a complete stop or significantly mitigated the speed.
But when the speed was increased to 40 miles per hour, the car stopped only 30% of the time. And when researchers looked at left-hand turns, every vehicle failed to stop. The same was true when the cars encountered another vehicle in an intersection. In every test, there was a crash.
Research has shown automatic braking not only struggles at higher speeds, but also in the dark.
The Insurance Institute for Highway Safety recently tested 23 vehicles approaching a pedestrian at night. Only 4 received a superior rating.
About half of the vehicles received either no credit or a basic credit rating, which is our bottom 2 ratings.
Despite the...
So I think the video was not meant to generally scare you, and I'm pretty sure you would have seen many such news about different safety incidents in last many years. But the fact is that the current AEB system, which uses the camera and radar, have limitations. So while it works, it doesn't work always. And I just want to give you one story from my experience that, a couple of years back, I was in Chennai to attend a conference. I started from Bangalore at about 6 a.m. and, by 11 a.m. I was here. So it took me about 5 to 6 hours to come to Chennai. And I finished the conference and I left to Bangalore at about 6 p.m. And while I started, it started raining. And by the time I reached Bangalore, it was 5 a.m. in the morning. So while coming back, it took me 5 to 6 hours. While going back during the rain, it took me about 11 hours. But the point I'm trying to make here is that I had an ADAS system which did not work for the 11 hours when I needed the most. Right? Every time I turn on the ADAS system, your assistant says, well, it's raining outside, I'm sick. And that's what we don't want, right? We want our ADAS system to be safer, we want it to be reliable, but we also want it to be available when we need them, right? So that's where we need to look at how do we innovate in newer technologies which will enable us with that.
As vehicles become more autonomous delivering passengers and goods, safety cannot be compromised, and almost simply isn't good enough. To deliver the automation of mobility safely, radar technology needs to be dramatically improved to perceive more. Digital radar is the vital sensor to perceive what cameras, LiDAR, and the human eye cannot see. Yet radar needs to be scaled up to a whole new level. At Uhnder, we've engineered a new paradigm for perception. We built the power and flexibility of digital processing into our radar sensors, enabling complete programmability. applying advanced digital signal processing, mitigating interference, to transform sensing capabilities altogether across all light and weather conditions for faster, further, sharper, better perception. And now, for the first time in the industry, Uhnder digital imaging radar technology is available on a chip, customizable, programmable, and fully integrated. And we don't stop there. Our proprietary technology delivers precise and accurate digital perception across complex scenarios, detecting pedestrians next to metal objects when still or in motion, distinguishing between distant objects in motion at different elevations, recognizing tunnels and road hazards to make the ride safer for all. When it comes to perception, almost simply isn't good enough. Perceive more with Uhnder.
Okay, so the main point here was that the current radar or the current AV systems does have a limitation, and it's not a unique problem that Uhnder is trying to solve. There are regulation body like the NCAP and the NHTSA. They are improving on the test coverage. They're adding these newer complex scenarios to the NCAP. If you read the NCAP 2030 roadmap, most of the complex scenarios that you saw in the video, they are being reflected in the NCAP guidelines. We also saw that the imaging radar shows a lot of potential because it allows a safe driving or an ADAS feature at a very complex scenarios. And the most important thing is that the imaging radar works under very difficult weather conditions. It also works under difficult lighting conditions where most of the time the camera would fail. So you need a radar system to accompany a camera sensor. And finally, last but not the least, the imaging radar sensor is a much cheaper and smaller compared to the LiDAR sensor, which is another alternative. But again, we are not talking about a premium feature here. We are talking about the most mandatory AV system that we need to have in the car. So we want this feature to be available in all the car, and cost is going to be one key thing. So now, having understood that imaging radar is critical for the ADAS application, we need to also understand what exactly is an imaging radar and how it differs from the current radar that we have in the market. And most of you know, and given the broad audience here, the radar has been used in the industry for more than 100 years. It has been used in aerospace, defense, and space, but the basic fundamental concept remains the same. So a typical radar would transmit a very high frequency signal. We call it as a pulse or a chirp at say about 77 gigahertz, and it transmits and receives the reflected signal back from the radar, and based on the time of flight from the reflected target, it estimates what is the distance. So in the case of the aircraft, it monitors how is the movement of the aircraft, whereas in the case of the automotive, it looks at what is the object in front of the car, whether to apply braking or whether not to apply braking. So that's the first dimension of the information that radar gives. But when you repeat this pulse and the chirps again and again, you get a very precise estimation of the velocity or the relative velocity. So now you know that the person or the object in front of you, whether it's a car, because if it is a moving car, or it's a pedestrian, that gives you a lot of information, because when you're trying to apply a braking system, you want to know how fast are you approaching the other car. And that is a key information that radar can provide you very precisely. But at this point, you still don't know whether a car or a pedestrian is in just exactly in front of you or it's in a different lane. And that's where the third dimension comes in, which is the azimuth angle. Now with the azimuth angle, you have three dimensions: the range, velocity, and also you know that the object in front of you is in which lane. And currently, most of the radar that you see in the market, they are called 3D radar, right? The fourth dimension is the elevation angle. As you saw in the video, to detect a car just next to a tunnel or a bridge, you also need to know what is the elevation information. And once you have that, you can handle so many complex scenarios. So while there is no standard definition for what is an imaging radar, most of the companies refers imaging radar as a 4D radar, which provides you the range, velocity, the azimuth, and the elevation angle. And the key thing here is that to get this azimuth and angle information, you need to transmit from multiple transmitters and you need to receive the data from the multiple receivers. And how reliable is your angle estimation depends primarily on how many transmitter and how many receiver channel you have. So in traditional radar, you have about 3 transmitter and 4 receivers, so you get about 10 to 20 degree of separation. But for an imaging radar and for the complex scenarios, you need 1 degree or sub 1 degree of resolution. And that basically means that you need much more number of channels. So what are the challenges now, given we know that the traditional radar has a limitation in terms of how reliably they can operate? To get to the imaging radar, we need to get to 1 degree of resolution, and 1 degree of resolution means that you need 10x more channels than what we have, right? So you need increased number of TX and the RX channels. And how do we get to that 10x more channels? Typically what we do is that we take one 12 channel radar or a 16 channel radar and we put 8 of them in an array, and then we put another controller which kinds of synchronizes them. But remember, the radar is operating at 77 gigahertz, and synchronizing them at that frequency is not an easy task. And also these radars are a completely different sensors, and to synchronize them we also need to calibrate them almost on real time. So that's again a very big challenge if you have a multi-chip solution. Third thing is about the increasing requirement. So with the 3D radar, you get to see like tens of cars in your lane, in the next lane. But with the imaging radar, you would see thousands of objects. You would see the car, you would see all the pedestrian, you would see the signboard, you see the trees around it, you see the static objects. Pretty much you get a visual image of the entire road. And now to process the data, you need a much more compute in your system. And finally, to handle the complex scenarios, like to detect a pedestrian next to a car or to detect a pedestrian next to a guardrail, those complexity you can only handle with certain advanced algorithms. You want to classify everything that you see, whether it's a pedestrian or it's a car, so that you can take the best driving decision. So you need to have some algorithms and AI built into your sensor. So these are mostly the internal challenge related to technology that we need to solve. But other than the internal challenges, the radar also has a lot of external challenges. And we mostly talked about that the radar generally is very robust when it comes to weather, but we still need to monitor that the radar is performing well even against different weather conditions. Interference is another big industry topic right now for radar, because there are going to be 3 to 5 radars on every car. And once you have so many radars in different cars, each of these radar signal also you will receive. So you receive the signal that you transmit, but you also receive the signal that the other radars are transmitting. So how do you mitigate or how do you handle this kind of interference is a big topic, and that we need to solve. Similarly, the multipath, the sensor alignment, there are many other general sensor related challenges that we need to handle here. But last is also very important here, because the industry, and it's nothing specific to the radar, but the automotive industry, we call, right, automobile is becoming like a mobile phone now. You need automobile to deliver a feature almost every year. We want a new radar to be added. We need new features to be introduced pretty much every year. And right now, OEM relies heavily on the software updates, to roll out these features. But as we discussed in the morning session, while this flexibility is good, but when we are talking about the safety critical application, we need to be very careful about it. So those are the non-technical challenge that we need to resolve. Thankfully, the automotive industry has matured, the process has matured over the time, and they have defined at least the key pillars that we need to talk about, and this is pretty much the theme of the summit. The functional safety, security, and reliability. You need to have a solid foundation in your company to build a radar or any other automotive product. So how do you build the functional safety and security into the imaging radar? So this is a very high level architecture of the imaging radar. As we discussed, we obviously need to have much more higher number of channel. Say 96 or 128, so from 12 to 16 we need hundreds of channels, so that's one thing to be integrated. Then we need the analog and the digital hardware blocks. These are the components which are going to send and receive the radar signal. Then we need a digital back end, which is going to process the data in 4 dimensions that we spoke. So the range, Doppler, azimuth, and the elevation information. Then we need multiple processor. We call it as the radar or the application processor. The radar and application processor is responsible to control all the hardware blocks. And also, as we discussed, we are going to get thousands of the detections. How do we know that these detections are a car or a pedestrian? So that classification and tracking of each of these targets has to be done by the application processor. Then these are mostly the functional aspect of the radar. And as we discussed throughout in the morning session, we need to have the functional safety and security embedded into the sensor, and it's not a outside topic. Security is key here because the secure boot is responsible for putting the entire software to start running, and it has to ensure that when the sensor starts running, it is in a trusted state. And it also has to provide the prevention and the protection against all the possible security threats that we discussed in the morning. And finally, we need an independent safety processor whose job is to monitor all the possible, the random hardware faults that you can have in the system, and as well as all the systematic faults that you can have system, to ensure that the software that are running on these application cores, they are running the expected core and they are not stuck, in kind of a loop. And finally, the important factor for radar specifically is that given it's also susceptible to the environment, it also has to monitor what are the coupling with the environment factors such as the interference. So given I want to give a bit of a context of the technology, I want to bring into what kinds of failures we are talking about here, because when we talk about general purpose sensor, we have a set of monitors that we have, but when we are talking about radar, the radio transmission and reception is the key. But how do we ensure that we are transmitting enough power so that we can, say, detect a car at 200 meters, or we can detect a bike at, say, 150 meters? So we need to monitor that. And then we are saying that in the imaging radar, we would integrate hundreds of channels. How do we ensure that these channels are not interfering with each other and they're not saturating each other? So typically a safety architect in the company would look at all of these functional requirements and will look at what are the critical aspects of the functional safety, and it will come up with a list of the monitor functional the safety monitor that you need. But broadly they are we can categorize them into two. For example, here the TX power monitor. This is one class of the monitor which monitors a particular circuit pretty much all the time, 100% of the time. But you can't monitor the entire sensor all the time because you need your sensor to also do a functional operations. So in that case, what we do is that we monitor them periodically, and one of the examples that we do is that we use a loopback system. So what we do is that we send a known signal, with a known frequency, with a known code, with a known time of flight, and then we fed back this signal to your other part of your hardware. And once we process the data, when we get the 4 dimensions of your the data, we look at the code, we look at the frequency, we look at the range and Doppler, and then we compare this with the known value. And if they match, we know that our circuit is working fine. If not, we know that there is a possible hardware failure or a software failures, and we are going to take action on that. But having done all of that, I'll be very happy that I have a robust imaging radar software. I have built in so many monitors. But when a tier 1 comes to us and say, how do I know that is that radar safe? You have listed down 20 monitors. There are advanced algorithms that you have built in. But how do I trust? Every company shows me these set of monitors, this set of fancy algorithms. The point is that how would you even judge whether they're reliable? But thankfully, the functional safety generally is in the automotive is not about claims, right? It's not about how many monitors you have. It's about a process. It's a standard. So whatever claims that we make, we have to justify it with the data, right? So that's where the two key pillars of the functional for the safety. ISO 262 is well known in the industry. It has been there for more than 10 years. And this talks about the general failures in the automotive with respect to the electronic components. ISO 21448, this is mostly with respect to also taking the component failures to the operating environment. So it also considers all the factors with respect to the the operating environment, such as how is the operator going to use it, how is the environment, for example, weather and rain going to use it. So in the context of radar and ADAS, this is one of the major focus now in the industry, that it doesn't work. Sometimes we have to also ensure that it works across different operating environment that it claims. So this is a busy slide on functional safety. I don't want to go into details because I'm pretty sure most of you are aware of ISO 262. But the key point I'm trying to make here is that ISO 262 makes a very distinct classification of the safety level from ASIL A, B, C, and D. And for each of these level, it also provides you the guidelines and also a matrix to meet. For example, a company like us, like a radar supplier, has to do the complete analysis based on the monitors that we have and what kind of a coverage that we can give for a single point fault or for the latent fault. And if this matrix meet a certain requirement from the ASIL B or a C, then we can go and stand behind the data. But other than the quantitative analysis, we also have to do a qualitative analysis to ensure that there is no coupling factor in the design, there is no common cause failure, and things like that. Right, so that's pretty much ensures that we have a safe system and we go through the compliance. But that's pretty much the first inning, I would say. Right, we have a good product like an imaging radar which shows a lot of potential. We had a lot of challenges, and we have an ISO 262 which seals us from that. So pretty much we have a good start. But how do we kind of defend this, a good start, right? We need to also perform well in the second inning. And the second inning is all about how do we defend ourselves and how do we ensure that we have a secure system in place. Typically, when we talk about security, we always feel that security is all about, the IoT or about a web transactions that we are doing. But think about a security breach in an automotive sensor, right? What if I tell you that the radar data that I transmit and receive, that itself can be spoofed, right? And there is a research that happened, and I have a next slide on that. But other than the radar spoofing, there are other threats that we discussed. These are general embedded security topics, that how do we ensure that the sensor, when they send data to the ECU over the CAN or the Ethernet, that data is not being unauthorizedly accessed, or how the data is not being tampered. So all of that security threats has to be handled. We also have to ensure that the system, there are fail-safe mechanisms so that our communication is not broken. And the key point here is that the security breaches impacts the customer confidence significantly, and any radar supplier or any automotive supplier keeps the security as one of the paramount importance. So this was the example that I was talking. There was a research done last year in Duke University. This was also published in IEEE last year. And what it shows is that the red car here, which is the attacker, can receive the signal from the victim vehicle and can somehow modify the signal and create a spoofed vehicle. So while there is no car, I receive the radar signal, I modify that signal, and attacker sends back the signal. And now the victim car sees suddenly there is a car in front of it, and it applies the braking, right? The other case is even more serious here, because what attacker does is that it jams the signal from the other real car, so that the victim car doesn't even see a car in front of it, right? That could be even more dangerous. Now we know that what kind of a safety hazard it can lead to. Under DCM ARC, we use something called a digital code modulation. This has been introduced first time, in the industry. So all of the radars in the market is something called an FMCW radar. So there is no modulation to that, but we use a digital code modulation. What it means is that anytime we send a signal, right, that has a unique code to it. So when we receive the signal back, we compare that whether I am receiving the unique code or not. If there is no unique code that I transmitted, I am going to reject that. So with that ensures that it's very hard for a spoofer, somebody who is spoofing my signal, to replay the same data. And even if it does that, I am going to change my code almost every 100 milliseconds, from one radar cycle to another radar cycle. So by the time he can spoof the data, I'm anyways not using the code. So pretty much very robust to the spoofing. And let's talk about the general, I think the security, features that we need to have in any sensors. Secure boot is one of the most critical aspects to the security, because the job of secure boot is to verify and load and then execute all the software that is eventually going to run. And most of the time the secure boot is not one stage. It typically is 3-stage process. So secure boot is usually will be lying on a secure part of your memory or your chip that loads, verifies and execute another software called the boot manager. We also call it secondary bootloader. And then that loads, verifies and executes all the firmware and the operating system, and finally all the algorithms that you're running in your system. And the key thing here is that all of the images has to be signed in a secure manner, to ensure that there is no non-repudiation of the code. As I said, the code signing is one major aspect to ensure that you're running the authorized, the code is secure. And typically the code signing is not a single step process again. Most of the time the tier 2 like us, when we build the chip, we provision our software or the firmware that we give, we provision it with a key called the tier 2 keys, and then we ship it to the tier 1. The tier 1 receives this, the SOC, they write the application software, they write the algorithm, and they want to protect their software. So they provision the tier 1 keys, and then they deliver it to the OEM. OEM receives the SOC, they want to add some new flavors, they want to build it an AEB or the emergency steering application, and based on that they add their own secret sauce and they want to protect that, right? So tier 2, tier 1 and OEM all have something to protect, and they have to go through this life cycle. The point here is that we need to ensure that when the device goes out in the market through this whole life cycle, we provide the right access to the tier 2, tier 1 and OEM, so that any sensor that goes on the field is very robust from spoofing. And finally, last but not the least, I think the communication, as we discussed, we have everything now connected car. The sensors are connected to the ECU over the CAN or the Ethernet. And we need to ensure that all the data that is being sent from sensor to the ECU, they are encrypted and they're also authenticated. We also need to protect against the denial of service attacks. We are talking about safety critical. What if somebody can just block the CAN, as we saw in the morning, right? If somebody can block the CAN, I should have a failback kind of a mechanism so that I can still send this safety critical information back to the ECU. So the redundancy and the fail-safe is equally important. So like the ISO 262, again, cybersecurity is not about claims. It's again about a process and a standard. So ISO 21434 provides a comprehensive frameworks for managing the cybersecurity risk throughout the life cycle. And I don't want to get into the details because we have seen enough in the morning. But the key point here is that the ISO 21434 has been developed in the footstep of ISO 262. And any organization who has developed the framework for ISO 262, it's very easy for them to also deploy 21434 because at least the process constructs are very similar. And this is pretty much the last slide. To get to ISO 262 and ISO 21434, the compliance is not an easy task for any organization to go from level 0 to full compliance. And typically the way we do is that we set a goal and we execute on those goals. We analyze the feedback, we analyze the result, we take some corrective action, and we set a higher goal. So we start maybe with getting just the process compliance, then getting into the A-level compliance. So all of that has to be done in a cyclic manner to finally achieve the end goal. And even after once we have done this compliance, we have to implement this at every project in the organization. And the quality assurance has to ensure that the implementation of these two processes, ISO 262 and ISO 21434, is done efficiently, and they have to keep monitoring all of the guidelines from the ISO 262 and ISO 21434. To summarize, the imaging radar is a critical sensor for the ADAS and all the autonomous driving applications. The fact that it works in many driving conditions where the camera and the other technology fails, it has a much significant advantage. The safety and security is not about claims, it is about a process. Compliance to ISO 262 and 21434 is essential to mitigate any risk. But ISO 21448, which talks about the safety of the intended function, is important to ensure that the safety is also achieved at the end function level, and that cannot be ignored in the system. Thank you.